So, in the next previous lecture, I have discussed about different indirect methods, and today I will discuss about another exploration method, that is geophysical soil exploration. Now, before I start the geophysical soil exploration, so these are the indirect methods. If I summarize all the indirect methods that I have discussed. So, first one I have discussed about the standard penetration test. So, that where a borehole is required, in the borehole we are placing a split pun sampler tube, and with the drill rod we are applying hammer blows on the split pun sampler tubes, and we penetrate that sampler tube into the soil, and then we count the number of blows required for 150 millimeter penetration. So, there are 3 150 millimeter penetration, and we neglect the first one and we consider the second and third one. The summation of this third and second number of penetration required for each 150 millimeter penetration is called as N value or SPT value, and then we apply a number of corrections that we have discussed for as per the IS code and as per the American code. So, and then this is the standard weights and with standard height we are applying the hammer blow. So, this is SPT, and then we discuss about the cone penetration test, where there are two types of cone penetration test. One is dynamic cone penetration test, another is static cone penetration test. In the static cone penetration test, we are pushing the cone into the soil and we are measuring the cone resistance or tip resistance and the friction resistance. And in dynamic cone penetration test, we are applying the hammer blow into the cone and we are driving the cone into the soil, and number of blows required for the 100 millimeter penetration is recorded. So, and then the next one we discuss about the pressure meter test, where a cylindrical probe is inserted into the borehole and the pressure is applied. With the application of the pressure, the volume of the probe or the cavity or the borehole increases. So, that volume increase is measured. So, ultimately we will get pressure versus volume curve, and from this curve we identify 3 different zones, and from 3 different zones we got P0 PF value and PL value. So, with the help of this P0 PF value and V0 and VF value, we got the pressure meter modulus. So, these modulus are also calculated, and based on that we determine the various soil properties. Similarly, the SPT-N and the CPT resistance also we use to determine the various soil properties. Similarly, we discuss about the dilatometer test, where a nitrogen tank is used to inflating the membrane. So, here where the which is similar like a pressure meter test, where this is the a flexible membrane where the inflating, which is this membrane is inflating with the help of the nitrogen. So, that resistance, the pressure, initial pressure and the pressure after the expansion is recorded, and based on that we determine various soil properties like the K0 value, over consolidated ratio, then elastic modulus of the soil, undrained cohesion of the soil. Then next one we have discuss about the vein shear test, dilatometer test. Then the next one we have discussed about the vein shear test, where the vein is inserted into the borehole and then a torque is applied. This torque is measured, and this vein height and diameter is measured, and with the help of this measurement we determine the undrained cohesion of the soil. It is suitable for the soft clay. Now, and these are the all tests where the SPT or standard penetration test, then vein shear test, pressure meter test. Here the boreholes are required, the instrument is inserted into the borehole, and where the CPT cone penetration test and DMT dilatometer test, where it is pushed into the soil, or in CPT also it is this cone is driven into the soil, but borehole is not required. So, these are the all tests that I have discussed, common in situ tests that we are conducting to determine the soil properties. Then we have discussed the different sampler tubes, because these are two types of sampler tubes. One is thick wall samplers, which is split pun sampler, and then the thin wall sampler, which is shell by tubes. And we have discussed that the sampler tube which is attached in the SPT, which is the split pun sampler tube. So, and we have already discussed this, if I collect the soil sample with the help of this split pun sampler tube, then the soil is highly disturbed. So, the soil sample that we are collecting with the help of SPT, which is the disturbed soil sample. So, and then we talked about the criteria to collect the undisturbed soil sample, and we can use the thin wall sampler tube to collect the undisturbed soil sample. And in the boring also we have discussed that we can collect the soil sample by boring, and whenever we can, if I want, we can collect the soil sample by using the sampler tube also. So, these are the two sampler tubes generally we use to collect the soil samples. One will give you the disturbed soil sample, another will give you the undisturbed soil sample. So, now today I will discuss the next exploration, next type of exploration, which is geophysical exploration. So, there are mainly three types of geophysical exploration. One is seismic reflection survey, another is seismic refraction survey, and seismic cross hole survey. So, there are I mean, depending upon the position of the receiver and the source, it can be seismic downhole survey, seismic uphole survey also. So, but I will discuss about these three seismic geophysical exploration. Now, the question is why it is called the seismic, because the procedure of this seismic, first I am talking about the seismic reflection survey. So, the procedure is that we there is a source where we are generating some wave, okay, and we are placing some receivers which is called geophones at different intervals, and from this source the wave which is generated will be received by this receiver. So, these receivers we are also placing on the surface, and the source is also on the surface. So, how these waves is received by the receivers? It is received by the reflection of the ray from the soil to different soil layer interface. So, because as we have two different soil layer, so this ray will reflect it from this interface, and we measure these reflected rays time period, at what time these rays are received by the geophone after it is generated from the source. Now, this so now why it is called seismic, because when there is the earthquake, there are different types of waves are generated. So, there are mainly two types of waves are generated. One is the body wave, another is the surface wave. Now, these body waves are two types. One is the P wave or primary wave, and S wave or the shear wave or the secondary waves. So, here basically we are generating these body waves in the source. So, either we are generating P wave or we are generating the S wave. So, that is why these waves which is generated in the seismic during the seismic activity or the earthquake. So, it is called the seismic reflection survey. So, here you can see that this is the so that means how these waves are generated. So, waves are generated, there is a possibility that we can do a small explosion. So, that is we can do, but it is a small explosion, or we can make some hammer blow. We can see that generally this is the common technique we use, that this is a plate where we are placing a hammer in this way, and these are the geophones which are placed certain intervals. These geophones are receiving the time required to the travel this wave from the source to the receiver or the geophone. So, they are basically measuring this time. So, now if I apply the hammer blow in this way, then the wave which is generated is reached with P wave or the primary wave. Now, if I apply a hammer blow a different way like this, suppose we have a so, we have a iron block and we are applying this hammer in this way. So, this is the iron block, we are placing this iron block on the soil and we are applying the hammer blow in this side of the iron block. Then the wave that will be generated will be reached with S wave. So, this will give you the P wave and this will give you the S wave. So, this is the reach with P wave. So, either depending upon how we are generating the wave, we can measure the P wave or the S wave. What we are measuring actually? We are basically measuring the velocity of this wave, either P wave or S wave, and the thickness of the soil layer. So, first if I discuss about the how these things we can measure, how we can measure these wave velocities and the thickness. So, we have to derive expression. So, let us derive those expressions, then you will understand how we will determine these velocity of the waves and the thickness of the soil layer. And from this velocity of the wave, we can determine the other soil properties like the shear modulus of the soil or the bulk modulus of the soil. So, let us discuss about how we can measure these properties. So, first suppose this is the ground surface. So, this is the wave, that is the source, and here we have one geophone or that is the receiver, and we have another soil layer. So, this is the layer 1, this is the layer 2, and as I mentioned, we can generate the P wave or S wave depending upon how we are applying the hammer blows. So, suppose in all the derivation I am doing, with that we are generating the P wave. So, we will take velocity of the P wave, and if I generate in other way by putting the iron block and apply the hammer blow inside of the block, then that will generate with the S wave. And so, but here I will derive all the equations with the considering that we are generating the P wave, but if you generate the S wave, then all the velocity of the P wave will be replaced to the velocity of the S wave. So, now this is the layer 2 and we assume that the velocity of the layer 1 is V p 1 and this is velocity of the layer 2 is the V p 2 and the thickness of this layer is Z. Now, this is the two layer interface. Now, when there is a source, and so when there is a source, that the infinite number of waves will be generated in the infinite direction, because the wave will not generate in one particular direction. It will generate, say it will generate in this direction, it will generate in this direction, it will generate this direction, any direction. So, but we will consider one particular wave. So, that will go directly from here to here. So, this is one possibility, that the wave will travel from the source to the receiver directly, and if this distance is say x or x n. So, then we can measure. So, here what we are measuring? We are measuring the time required this direct rays to travel from S to R. So, if we measure that time, so geophone will measure this time. So, that means, if I measure this time, so then the velocity of the first layer B p 1, so that will be equal to x n divided by T d. T d is the direct time required to this wave travel from S to R. So, this way we can determine what is the velocity of this wave in layer 1. So, that is we can measure. So, that means here x n is known, T d will measure through the geophone. So, we will get the velocity of the first layer, and this x n is known because we can place geophone as a known distance from the source. Now, there is another wave. What will happen? This will come here and it will reflect and it will go and receive by the geophone. So, why I have considered this wave only? Because of the position of the geophone. If I change the position of the receiver or the geophone, then a different wave we have to consider, but the things remain same. So, that is why. So, suppose this angle is I. So, this angle will be I. So, this is the reflected rays. So, that means we are measuring this reflected rays. Now, if I call this will be the x n divided by 2 and this is the z. So, I can write that tan I is equal to x n divided by 2 into z, because this is the I, this is x n, this is z. So, tan I will be x n by 2 divided by z. So, this I will get I. Now, similarly, we can write that, or if I write this is O. So, we can write S O equal to R O is equal to z square plus x n by 2 whole square, because this is z, this is x n by 2. So, this one will be z square plus x n by whole square. Now, the time required of this reflected rays, D means the direct, R means the reflected. Now, times required for this reflected rays will be equal to 2 S O divided by V P 1, because S O is equal to R O. So, 2 S O divided by V P 1. So, I can write 2 V P 1 root over z square plus x n by 2 whole square. So, this is that. So, now, how can I determine the V P z? So, the z will be equal to half root over V P 1 T r square minus x n square. So, this will be half V P 1 T r square minus x n square. So, V P 1 I will get from equation number 1 and this is the equation number 2. So, and z I will get. So, this is equation number 3. So, z I will V P 1 I will get from equation number 1, T r I will measure through the geophone, x n is known. So, we can get what is the value of z. So, this way we can determine the velocity of the first layer and the velocity and the thickness of this soil layer. Now, the problem is that here we have considered only one geophone. Now, if I use only one geophone data, then there is a possibility that we may get more error, because that means that there is a possibility of measurement error. So, rather than using one particular geophone, if we use say n number of or more than one geophones, and then the possibility of the error will reduce. So, that is why using one geophone we will use n number of geophone. Now, if we use the n number of geophone, then if in that case if I draw a particular graph, and that graph will represent that x n and the t. T may be direct, T may be reflected. So, and this is the 0 0 and x n will indicate the position of each geophone. So, this is the R1, in that case this may be the R2, so this may be the R3, so this may be the R4. So, in this figure I have shown that there is a number of geophones we are placing with certain interval. So, now in that case, and every geophone, in case of every geophone we get this type of expression. So, what will happen that for every geophone there is a direct ray and there is a reflected ray. So, now we have basically three expressions, basically we have two expressions, and this is the a different form of expression 2. So, if we have two expression of time, now if I draw the first expression of the time, so this is the x1, so xn1, or this is xn2, this is xn3 and up to xnn. So, that means here, so now for this first expression we will get this type of curve. So, if we will get this type of curve. So, point may be in this form. So, that means we will get a base fit curve. So, these are the points, because these are the points. So, that means time required to travel directly from the source to this geophone which is placed as xn1 will take this time, and for the xn2 this is the time required to travel the wave directly from source to the geophone. So, similarly, this is TD1, this is TD2, this is TD3. So, we will get a straight line where we are getting the base speed curve. So, possibility of the error will reduce. Now, once we get this curve, so the slope of this curve will give me 1 by Vp 1. The slope of this curve will give me 1 by Vp 1. So, instead of using a particular geophone data, so if we have a n number of geophone data, then we draw these points in a graph x versus t, then we will get a straight line. So, this will represent the equation number 1. And if I get the slope of this curve as this straight line, it will give me the 1 by Vp 1. Now, next one, if I draw the similar curve for equation number 2, then I will get, if I use a different color, so I will get a curve which is in this form. So, this will represent equation number 2, because this form this expression. So, this will give you Tr versus xn. Okay. So, but this will give a, this is the equation 1 is a hyperabolic, equation 1 is a straight line, and equation 2 will give you a hyperabolic curve. Now, from here, so if I extend, so how I from here I get the z value. So, if I extend, so suppose I will get this curve up to here, this point. So, if I extend this curve here, so this will give us a value which is T r 0. T r 0 is a value where the x n is equal to 0. Now, if I put this value here, so there I will get z equal to half root over Vp 1 T r 0 square, because x n is 0. So, it will be half Vp 1 T r 0, or you can get from this here. Here also this will be your x n equal to 0. So, you will get your z will be T r Vp 1 divided by 2. So, this T r 0 is this value, this is T r 0. Okay. So, from here I will get the z value from the curve also. Now, there is a the problem of this test is that, so we have to measure two different rays travel time. One is the direct ray, another is the reflected ray. So, this is the problem, because here this is a difficult task. No? So, which one is the direct ray, which one is the reflected ray, it is very difficult to judge. So, that is why to remove these limitation we will go for the seismic refraction test. Another one, in this test what we are doing, we are measuring the thickness of the first layer and the velocity of the first layer. So, but if there is n number of layers, then our seismic refraction rays is more suitable. So, I will discuss that about the seismic refraction ray surveys in the next class. So, in this class also, so this is the one limitation, that you have to measure two rays, and identification of these two rays is sometimes difficult. So, to avoid that, we have to go for the seismic refraction rays. In another way, even if we use this test, so drawing a hyperbola graph is very difficult rather than drawing a straight line. So, instead of drawing a hyperabolic curve, if I draw a straight line, then in this curve, then it will be better. So, how we can do that? So, instead of this curve, what we are doing, that we have a expression 2. Now, if I square this expression, then this expression 2 square both sides, then expression 2 will become T r square is equal to 4 V p 1 square, then z square plus x n by 2 whole square. So, this is the expression if I square both sides. Now, if I further simplify this, this will be T r square equal to, if I take x n, so this will be the your x n square, then this 4 cancel out, this will be V p 1 whole square, this is V p 1, and then plus we can write 4 by V p 1 square into z square. So, now this is our expression number 4. Now, if I draw this curve, so instead of drawing x curve, x n curve, we are drawing x n square divided by T r square curve. So, now it will be a straight line. So, now this will be a straight line. Now, slope of this curve will give you 1 minus V p 1 square. So, this is equation number 4. So, because that means there is two ways, either you use this curve. So, where V p 1 we can easily determine, because it is a straight line, but getting the z value, it is a hyperabolic curve. So, rather sometimes it is very difficult to draw from the points a hyperabolic curve. So, it is why what we are doing, we are making a square graph, x n square and T r square, and now we are drawing this curve. So, the slope of this curve will give us 1 minus V p 1 square. So, now from here I will get the V p 1 value, and then how I will get the z value. So, again this will give this value will give T r 0 square. Now, if I put T r 0 square with x n equal to 0, so it will give T r 0 square equal to x n is 0, 4 z square by V p 1 square. So, z square I will get from here, z square is equal to 1 by 4 T r 0 square and V p 1 square. So, we will which is similar to this value also. So, so this is half into V p 1 into T r 0, but as it is in square form. So, directly we can put these values here, then we can take what is this, because V p 1 square we are getting from here and T r 0 we are getting from here, and then we will get the z value. So, instead of in the second method, instead of using two different curve, by one curve we are getting V p 1 as well as the z value, but still those limitations that I have discussed will remain. So, we have to remove those limitations. So, to remove those limitations, we have to do the next test, that is seismic refraction test, and in the next class I will discuss about the seismic refraction test. Thank you.